Hello, everyone. Hello. Thanks for attending this presentation. I am very pleased to be here with you. For those who had traveled, I hope you had a good flight. I hope you had a good flight. My name is Titiano. I am a system power management expert, and I co-founded the Baylibre company. Baylibre is an embedded Linux consulting company. And so I have 15 years of experience in embedded Linux. And I spent 9 years at TI in the OMAP mobile processor business, focusing on power management. 3 years ago, we created with few friends the Baylibre company. And since October 2014, the Baylibre company is involved in the Google ProjectARA modular platform. And among all the things we are in charge of, we are focusing on power management, which is the topic of this presentation today. So let's go over a short introduction. So you may know that the smartphones that are available today, they are most of the time available in one-size-fits-all, meaning that any new platform, any new smartphone you buy will probably have a complete set of features. Everything you could get of a smartphone will be integrated, whether or not you need or want it. Google is trying to redefine that assessment as part of the ProjectARA by creating a Linux-based platform where consumer may assemble the device they want with the module they want. As you can imagine, providing this flexibility comes with many challenges. And one of the challenges is power management. Because when you design a mobile platform, usually you pre-characterize and you optimize the power consumption of this platform. You know exactly your power budget. You know exactly how much power every component of this platform will consume. And you tune it to get the most power out of it. In the case of a modular platform, the PCs are not known in advance. It will be built by the customer, which means that this optimization and fine-tuning effort cannot be done. So this is really a huge challenge. And so we have to think about new ways to update the existing Linux power management with new solutions that could answer these kind of questions. How do we do runtime power management of module? How do we ensure that there is enough power to supply a module when it is inserted? How do we protect the platform from malfunctioning modules? How do we balance power over performances for connected modules? That's the sort of questions we need to answer now, that we don't need to answer in a regular platform. So the agenda of this presentation comes into 4 parts. First part, I'll explain some basics about the ProjectARA to better understand the next topics we'll discuss. It's going to be terminology and technologies involved in ProjectARA. Then I'll present a very high-level power management architecture of ProjectARA. And then we'll go through the main challenges and solutions we have identified. So we'll talk about runtime power management of modules, about the power management of the UniPro links between modules. We'll talk about the idle power management of modules, power allocation framework, overconsumption protection, as well as thermal management. And we'll close the session with some Q&A. A little clarification about the scope of this presentation. We will focus on the power management of the ARA modules, the brand new thing, not about application processor or the regular power management you'll find in a smartphone today. So we'll talk about the power management of the ARA modules, the SVC, the supervisory controller, as well as the UniPro network, the switch and the bridges. We'll not address, as I explained, the application processor because it's going to be exactly the same you have in any Android phone you have today. And as well, we will not talk about battery management because this deserves a whole presentation all by itself. Okay, let's start with some basics. Terminology, technology. For those of you who may not know exactly what ProjectARA is, it's a modular platform that acts as a phone but supports add-on modules. It detects the insertion of modules and control how it is ejected. We control the power that are provided to those modules on a fine grain. The platform provides a UniPro network. UniPro is the name of the high-speed communication channel used to connect all the modules together. This UniPro network has been specifically selected to balance power and performances on a mobile platform. There will be a manifest used to describe the capabilities of the modules. And we will also be able to leverage online sources to support modules if required, which means that if the Android running on the platform misses some drivers for some modules, we'll be able to download all the necessary drivers and other information online, on the fly. So a few words about UniPro. UniPro is the name of the high-speed interface technology that we use to interconnect all the integrated circuits on ARA. So it's a bidirectional high-speed connection. It supports multi-lanes, and it can go up to 5 gigabits per second per lane. So this is very, very fast interface. It is obviously low power because that's what we need for mobile devices. And what's interesting is that the speed of the UniPro links can be dynamically changed to balance power over performances. So this is I would say that this is one of the foundation technology used by ProjectARA. ProjectARA has been built upon this UniPro network. You may find more information on Wikipedia, for instance. And it is, UniPro has been created by the MIPI Alliance. So it is an alliance of all the key stakeholders in the mobile world. Graybus. The Graybus is a software library that has been created and is being developed by the ProjectARA team. It has been designed to abstract the communication between modules. So the idea is to provide a completely generic communication interface between all the modules, I would say a la USB. So typically we don't want to write software for UniPro. We don't want UniPro to be the unique communication channel available. And so we built this Graybus software library to abstract communication between modules. So it defines messages that are sent over a connection between modules. It supports operations that are pair of requests and responses. It defines protocols that are set of operations a connection may support. And it protocols implement classes of device behavior, for instance, GPIO, I2C, camera, speaker, or audio. That's classes, the same way we may have for USB. And so there are protocols defined for each class. And the module, when they are being plugged in the frame, they will advertise the kernel about what classes it supports. So already very similar to what's happening today with your USB device you plug into your PC, like a mouse, for instance. Your mouse will be automatically detected. It will be recognized as a mouse, and you may start using it immediately. That's exactly the same thing that will happen with a module on ARA. The good thing is also that Graybus is completely open source. So you may fetch the spec and the code on GitHub. I was mentioning a frame or endoskeleton. Well, this is the name of the body of ARA, the thing that you would plug modules to. So it's depicted here. And you see you have predefined sizes of slots of predefined sizes where you could insert and remove your modules. The modules will be securely locked, and you will need to, the user will need to ask module ejection. It cannot be removed manually. This is both up the front and the back side of the frame. So you may add and remove modules on the front and the back. So for instance, even the display could be changed on the fly. On the back, you may see you have different size of slots. The smallest one is what we call the 1x1. You have a slightly twice larger one, the 1x2, and then the biggest one, which is 2x2. And each slot provides at least what we call one interface block. So this is all the electrical signals needed to operate the module, so communication signals and control signals. All the slots and all the modules receive the exact same signals. So it includes also the power, obviously. So it's completely generic. Whatever you want to do, you still reuse the exact same signaling. So you have a control app. So to eject, so the question is how to eject. So to eject, you do it through a control application on your phone. Yeah, exactly. This is because it's securely locked, and this is to make sure the communication, there is no disruption in the communication. Yeah. Well, so today it's a control app, but it may change. Yeah, so you may notice also that for the biggest, so the 1x2 and the 2x2, a module may have two interface blocks. So that may be useful for modules that require more power than a single one, or may require also more data bandwidth. So it can double typically the power and double the bandwidth available. That's supported. Okay, I mentioned the SVC, or supervisory controller. So this is a tiny microcontroller embedded inside the frame that is in charge of all the module maintenance as well as the UniPro network maintenance. So this is the small microcontroller that will do the detection of the module insertion, that will take care of module ejection upon request from the Android application. It will power control the power supply to the modules, as well as do some power monitoring and protection of the modules. And in terms of regarding the UniPro network, it will be in charge of controlling the big switch that is aggregating all the connections, and also about configuring and setting up all the connections between all the modules. And finally, the modules. The modules, they are of different sizes. Again, 1x1, 1x2, 2x2. What is interesting to know is that it's not a one-to-one mapping. Modules may implement different features, not a single one. So for instance, we may incorporate multiple sensors in a module. It may include a camera, it may include a microphone, it may speakers. It's not limited to one function. And there is no limitation, I would say, per requirement. It's not limited. Any module, I mean, any functionality you want to provide, you may think of, is supported, or could be supported. So making the link with the gray bus, in the gray bus terminology, a feature implemented in a module is called a bundle. And so a module may include multiple bundles. And as I explained just before, a module may receive one or more interface blocks, and these interface blocks are called interface in the gray bus terminology. So in terms of the block diagram, a module can be represented by interfaces from which different bundles could depend on. The interface will be the communication interface with the frame, and the bundle will implement the functionalities. So usually you may find on modules a UniPro bridge, so it's a chip that is talking UniPro on one side and whatever needed on the other side. All the current existing communication bus, for instance, I2C, GPIOs, I2S, SPI. We don't yet have native UniPro support for all of these kind of functionalities, so we need a bridge to convert UniPro to anything else. And so these chips, they are running an RTOS that is called Nutix. It's a real-time OS, and the ProjectARA is reusing it. Okay, so with this few information, we should have enough knowledge to understand the power management architecture of ProjectARA, which is depicted here. So don't be scared of all the connections, but it might be a little too detailed. But anyway, we still find a frame that includes the SVC, the supervisory controller, and the UniPro switch with all the UniPro ports. And then we have modules that are connected to this frame through the UniPro connection. All the modules receive a reference clock as well as a main power supply and some other signaling signals. And then it's up to the module vendor to implement whatever needed. But it's exactly the same clock provided to all the modules, exactly the same power provided to all the modules, and the same control signals. Here you can notice that even the application processor, so the SoC running Android, is considered as a module, a regular module, and receives the exact same signaling. So it's very generic architecture. You may see that there are many different power regulators in the frame, and we'll need to take care of that as part of the power management. So in terms of what's controllable, what is not controllable, you may see that we can control the power regulator to the module, so we can turn it on, turn it off. We can also clock gate the reference clock to the modules. We have depicted here for each module for each slot there is a power monitoring chip that is used to make sure the chip is not over consuming, and we can also measure its power consumption at any time. So that's the high level architecture of power management architecture of ARA. So this architecture, given this architecture, now let's talk about the challenges and what solution we have found. So first, the biggest one is the runtime power management of modules. What we want to achieve is being able to dynamically power on, power off, or suspend a module, depending on the active use cases. So for instance, when we start the camera application, we want a camera sensor in a module to turn on. And when we stop the camera application, the module should also be powered off. So that's the kind of functionality we want to achieve. So by on state, we mean, so the module shall be on. So in the on state, when there is any active use cases requiring it. It should be turned off when there is no active use cases requiring this module. It may also be suspended. Life is not that easy. It's not just about being on or off, but sometimes for some use cases we don't want or we don't want to pay the penalty to completely shut down a module. We may want it to resume quicker than usually, and we may also want to keep the software state inside the module to keep it maintained. So that's why we support also suspend state, where everything is maintained and can resume faster. What is important to note is that this is always driven by use cases. This power transition only happens at the boundary of the use cases. That's different than idle power management that I will cover later. It is always initiated by the application processor. The module is never taking the initiative to self-power off or self-suspend. We really want the kernel to control the state of the module. And how we do that? Well, we simply integrate the existing Linux runtime power management framework, and we implement in all the Graybus class drivers, we will implement the runtime PM callbacks. And that is working because dynamically we will instantiate the Graybus drivers, and so dynamically we will instantiate and do all the things necessary to have the callback being called by the framework. So this is really nice, and this is really a powerful, I would say, really a powerful advantage of the Linux kernel, provided by the Linux kernel. So in terms of effort, what does it represent? Again, what's available today and without having anything to do is the standard Linux runtime power management framework. There is no single modification done to it. It's working perfectly. We reuse the dynamic loading of driver and instantiation. But what needs to be done is all the runtime PM support in Graybus, defining operations, defining all the allowed power state transitions and dependencies, integrate the callbacks, implement the callbacks in the Graybus drivers, add the support in the SVC, because this is the SVC that is controlling the power and the clock to the module, so it has to receive the right Graybus operation and implement it. And also as well, particularly for suspend, we want there must be some support added to the module, the firmware running in the modules. The next challenge is about power allocation for the module. The smartphones are mobile devices and they are battery operated. So it's not like if it was plugged into the power plant. It has a small power budget, and we need to carefully use it. And when you start talking about adding new modules inside a battery-operated device, you need to make sure that there is enough power to power on this device, because otherwise you may face brownout. So here we want to make sure that we have enough power at any time to supply a new module, to supply a new processing on a module, or to be able to eject that module, because the ejection will require some software, some hardware, and it has to be powered. Otherwise, the module may remain stuck in the frame. So what we need is a framework that includes a policy that is aggregating all the power allocation requests from all the Graybus drivers, and will decide whether or not there is enough power to turn on this device, this module. So when you plug in a new module, there will be some negotiation done, and the module may not be fully powered on or fully instantiated software-wise if there is not enough power. An important thing also that is pretty new is that the power budget is not fixed. The level of the battery is decreasing over time if you are not charging it. So when you have a fully charged battery, a module may be there might be enough power to support a new module, to supply a new module, but in case of low battery, it is no more the case. It may not be no more the case. So this is something to care about. And that's why also we have put in place mechanisms to constantly monitor the power consumption of a module. And if a module was exceeding the power it was allocated, it would be immediately shut down to avoid any disruption. Okay, in terms of import, while we started from scratch, what had to be done is to define this whole module power allocation framework. Again, add the support in the gray bus by defining new operation. Add support in the SVC because it's doing part of the job. And then in terms of what a module vendor may do, he may also need to characterize the power consumption of its module so that it can advertise the module power allocation policy about how much power it requires. The final step will always be the optimization of the policy. A little bit related with the module power allocation module allocation framework is the module overconsumption protection. We want to protect the frame or the endoskeleton. We want to protect it from a malfunctioning module or from some bad usage. So the idea is to implement a hardware shutdown that could, as soon as possible, power down a module that would exceed the allowed power budget it got allocated. And so this is all done by hardware without software intervention because for safety reasons. And this is not a fixed, the threshold of this overconsumption protection is not a fixed threshold. It's the one defined by the module power allocation framework. So dynamically, we will adjust the shutdown threshold. Again, we started it from scratch. We had to implement the complete support in the SVC firmware. So the driver of the power monitoring device. So that's how it is implemented. There is a power monitoring device that is able to shut down, that is programmable and may shut down the power supply. And so we need a driver for that. We need the power monitoring framework. We need to provide the right gray bus operation for that and integrate all this with the module allocation framework. Okay, so we addressed the runtime power management of module, the power allocation and protection. We can still provide more optimization in terms of power management by making sure a module is not over-consuming while it's doing nothing. The runtime power management of module, as I explained, is taking place at use case boundaries. But it doesn't mean that inside a use case, when a use case is active, it doesn't mean there is no idle time on the module. And that's, for this idle time, that's where we want to optimize the power consumption. And so that's the purpose of this challenge. And the idea is that we may use clock gating, DVFS, so clock and voltage scaling or power switching internally within the module. This is really dependent on the module architecture, and this is not at all done with awareness of the application processor or the kernel awareness. So this is the module firmware that will be doing some idle power management. And this is completely done without awareness of the application processor. So we leverage the Nutix power management framework for doing that. So NetX is able to transition drivers and the system into various low power modes that we have defined. And so that was our job, to find all the low power states we could put a module into, and implement all the callbacks of the new NetX power management framework, and do the optimization. Very similarly to the module idle power management, we also have to do the same on the SVC. SVC is a microcontroller. It runs on the same RTOS. It's running NetX as well. So again, actually, if you think about it, the SVC is idle most of the time. If there is no module being inserted or being removed, if there is no gray bus operation ongoing, it's doing mostly nothing. So we want the power consumption when it's idle to be the lowest possible. So that's what we have to implement here. And again, it will include clock gating, clock and voltage scaling, power switching. The thing to really take good care of is that the SVC, if it's idle, it has to answer requests and handle events. So it's able to wake up, the SVC has to be able to wake up from any of these events. And again, this is completely driven locally by the NetX RTOS, and the AP is not involved at all in this SVC idle power management. So I mentioned that the UniPro link are scalable and can be dynamically scaled to reduce power or to provide more data bandwidth. So this is what we want to address here with the UniPro link power management. The idea here is to, depending on the running use cases, we want to adjust the speed of the link. For instance, considering a module that is just implementing sensors, it doesn't require 5 gigabits per second bandwidth. It will require very few. Now, if you consider a camera module, that is no more the case, it will require very high bandwidth. So we want to be able to adjust the speed of the link based on the usage. And that's what we address here. So we will be profiling the modules, understanding. When I mean profiling, it means that actually the module will advertise the UniPro link power management framework about how much latency or how much bandwidth it is sensible to. For instance, again, if a module is implementing the camera class, we know it requires a lot of bandwidth. If it's implementing a sensor class, we know it doesn't require a lot of bandwidth. So based on all these hints, performance hints, the module will advertise the gray bus kernel width, will be able to select the right speed. And all these performance requests are aggregated again by a policy that is deciding. Because if we go back to the architecture, you see that there is a single link between the application processor and the UniPro network. So we need to aggregate all the requests for this module, and for all the other modules, and this link must perform enough to provide the necessary bandwidth for all the other links. So that's why we need a policy for that, and that's where the complexity is, by the way. So this is managed by software on the application processor, and a part of it is implemented by the SVC, because the SVC is in charge of the network maintenance, so including the setting of the speed. The modules are not at all involved, and we don't want a module to self-set their speed, because for safety reasons mainly. The final goal being that we don't degrade the user experience and optimize the power. This is again started from scratch. We have defined a complete framework, all the Graybus support, operations. We have integrated, we need to integrate all the bundle drivers with the framework and do some profiling to correctly advertise the policy, and then work on the heuristic and fine-tune them. The last element we haven't talked about is the UniPro switch. The UniPro switch is a big device that consumes a lot of power. We don't want it to consume power for unused, unnecessary things. So for instance, if a frame can handle 10 modules, it will provide 10 interface blocks. And so if they are not connected, we don't need to power this interface block. So we will do some reference counting and make sure that the UniPro ports that are not used are gated or powered down. We may put the UniPro switch into some hibernation state when there is no module connected or when the platform is suspended, and we will shut it down when the phone is shutting down as well. There are different techniques, power management techniques. It may include, again, clock gating, DVFS, or hibernation. Because the UniPro network supports hibernation. It's a state where it retains the link configuration, but saves power. This is purely driven by the SVC. The application processor, the kernel is not involved, and the module also are not involved. So the main job here was to add this support to the SVC firmware. The last challenges I wanted to address today is thermal management. You may have noticed that our phones are all getting warmer and warmer, sometimes too much. This should not happen, and this is exactly the same problematic with ARA platforms, except that it's a little bit more complex because you may have modules on the back of the frame. So the modules, that's the thing that may warm up the hand, and it's not included in the frame. So again, we need to modelize all this, and we can consider all modules as a thermal zone or as a cooling device. The modules that may have thermal issues should include a thermal sensor. And the idea is to integrate the standard Linux thermal management framework, modeling modules, as well as the frame, as thermal zones and cooling devices. So, and also we will use the UniPro network, the ability of the UniPro network to scale the speed, also as a cooling device. By reducing the speed of the UniPro network, we will also decrease the heat dissipation. So here it's a complete reuse of the existing Linux thermal management framework. It's only a matter of implementing it and again providing the right operations to Graybus and implementing this in the firmware. So it's a lot of integration work and then fine-tuning obviously once this is integrated. Okay, that was the last challenge I wanted to address today. Thank you for attending. If you had any question, I'd be happy to answer you. Yes, Paul.
So what percentage of the power management algorithms implementation are in the AP in the Linux kernel as compared to what's in, say, the microcontrollers that are running?
So everything, so all the intelligence is on the AP. I have addressed only the UniPro switch power management is purely handled by the SVC. The module firmware does not implement anything. It's a slave to the AP. And so all the policies, everything that requires tuning and that could be upgradable or updatable, everything, the idea is to have it on the AP because it can be updated with an Android update. So it's way more easier to update code on the application processor than on updating the firmware on a module or on the SVC. Yep.
Can you elaborate how the Rails protocol and runtime PM interact?
Yes. Okay, so the question is about how Graybus and runtime PM interact. So I'm going to go back to the slide of the power management architecture. Okay. So we are on the application processor, okay? That's where Graybus is, and that's where all the drivers are loaded and instantiated. So they implement the runtime PM calls. So anytime a callback, runtime PM callbacks, anytime a callback is invoked, that will be turned into a Graybus operation, okay? This Graybus operation, depending on what we want to do, but for instance, power on, power off, we will send a power on, power off operation to the SVC. We will also send an operation to the module to do some software maintenance first. But the idea is that there is a callback invoked, a runtime PM callback invoked on the AP. This is translated into a Graybus operation, a dedicated one or more Graybus operation that are sent to the given module and to the SVC. What do you mean by dynamic part? Yeah. Yeah. Yes. Well, if you say you do you call put, you call get. So you want the module to be on, okay? So there will be so that's generic name, but there will be a power on operation sent to the module and to the SVC, okay? There will be a response back, so it's all synchronized, obviously, and that's it. When you do the get, so you release the module, you don't want it anymore, that will be turned into a power off, for instance, operation that will be sent to the target and to the SVC, and the SVC and the module will implement it locally. Yeah. Mm-hmm. Yeah. Yeah. All the put, get, etc. All the things are being translated into Graybus operations. So it's not that difficult, conceptually. The thing is, the thing is to integrate all there is a lot of integration work, like all the various bundle, all the Graybus drivers, the class driver you will implement needs to implement that, and also on the firmware side. It's not going to be certified or approved, and yeah. So the thing is that so to answer your question about if a driver doesn't implement the callbacks, so don't forget that you are in Android ecosystem with certifications. So this will be probably pre-tested and pre-validated. I mean, you are free to do it on your own, like Cyanogen or whatever, but I think that all the things you will be able to buy from regular shops, retailers, this will be certified, and the power management will be taken care and tested. Yes?
Yeah. Do you have different profiles between the Platinum versus the JC?
Yes. So that's the purpose of this power allocation policy. It will monitor the battery level, if it's being charging or not, how many modules. So there are different budgets, actually. I should have covered that. But typically, overall, you have a total budget, what the battery can handle. But you also have a power budget per slot. Okay, you may not allow use all the power budget for a single slot. It is shared, and there are some electrical limitation. Okay, there are power regulators used. They can supply that amount of current. You cannot exceed that. So we need to take care of a per slot power budget and a total power budget. And the total one is monitoring the battery level, the charging, and other things.
So what happens in case where if you plug in a module that requires a high demand, power on AC, and then you unplug the AC, now the battery reserve is no longer.
So it's released.
satisfied.
Yeah, so you know it's like resource allocation. I mean, if it's the budget allocated, when the module is removed, will be released as well and available to others.
Well, I'm saying when you remove the AC.
Oh, okay, yeah. So then it's going to be re-evaluated, and potentially we will come into those tricky situation where you don't have the budget anymore, and so you may need to shut down. I mean, there are situations if you have no power, you need to shut down something. That's as simple as that. Yes, Paul?
Have the existing Linux power management frameworks, have they been good enough for you to do all this development, or have you needed to make patches to the framework code?
No. So maybe I haven't emphasized it enough, but we have reused the standard Linux framework with no single modification. So everything there described is still work in progress. So it's still ongoing. But so far, we haven't had to change anything to the existing. That's the power of that. I mean, that's really the power of Linux and how well designed it is, and why we love it so much, is that the things are well designed. You've been part of it. And so this is just great. I mean, the main thing were in place. We just added the modular aspect of it. And this is where it's not traditional. This is where it's completely new. We've been doing the same job. You know that you get a platform, you measure the power it consumes, you fine-tune things, and that's it. But it's static. Now, you have a frame, and then you plug in modules that consume maybe more power than anything else, and you have to deal with all these things. It can be added, removed. We cannot upfront do this characterization work. So that's big challenges.
Yeah, it seems like some of this work you've done can be useful for power management over a lot of different kinds of hot-level buses.
Yeah, exactly. The module power allocation, for instance, I mean, if you take it from a more generic aspect, it could be a bus power management framework. Maybe someday it will become part of Linux differently, but we will reuse it. But that's right. That's very right. Thank you, Paul. Any other question? Yes?
So how do you account for transient current being run? Do you have like a
Yeah. So how do we account for transient current? So this is again part of the certification process. I mean, just consider USB devices. When you plug in, this is accounted, right? So exactly the same. There will be certification. There will be specs published for that. And so a module should comply with those specs. And if it's not, it will shut down. As simple as that. Yeah, but I would say that this certification process is very useful because we know we are in a safe environment. No more question? Well, thank you so much for attending.